the last person to talk about Bernoulli, and I'm going to talk about the other bane of the mechanical engineering student's existence, and that's Euler. He started a version of math called calculus of variations, and what it deals with is a function of functions instead of a function of variables. And so what you end up with is an extremely complicated set of equations that you're looking to either maximize or minimize. Now there's two different methods that are used, and he developed both of them. The indirect method, which solves the general theory of partial differential equations. You basically take the difference in the two equations of motions, you integrate them, and that becomes your differential equation. What I've shown here is the Hamiltonian, which was developed by Petragan in the early 60s, and then followed on with significant work in offline optimization, because this is very difficult to implement and especially difficult to program. So what I'm going to be using is the other version, the direct method, which was also developed by Euler. But the problem is that what we do is we assume that the solution can be visualized as the form of a number of linearly independent functions can be added together to create our solution. What this does is it limits the ability, our ability to find the actual optimal solution, because instead of just taking the actual differential equations, we're assuming a form. So we're going to limit ourselves, and we can only come up with a quasi-optimal, a near-optimal. But the calculation advantages of this are significant. And this is computationally easier, but it's significantly more numerous. And so it needs the development of computers to be able to process this sort of data. So Professor Taranenko, who's a Russian in the 60s, first applied this concept to aerodynamic vehicles. And what he did is he said, we can assume that the reference function can be written as a sum of a finite series, and that is that reference function is going to be the flight path of the vehicle. And he suggested the following shape of the unknown function, and that function can be anything, though, as long as it satisfies the boundary conditions that we're going to talk about here shortly. And then once you have that function, once you have that trajectory, instead of integrating the time histories to develop the trajectory, you go the other way and you take the trajectory and figure out the time histories necessary to get that. And that's called the inverse dynamics approach. And the key to doing this is this variable right in here, which is the tau variable, which is we call it it's a virtual arc. And it can be any continuous monotonic variable. It can be time, it can be distance, it can be speed. Whatever your situation demands, we're going to talk about that. It's virtual. It doesn't really exist, but we're using it to correlate other options. What this does is it allows us to separate the time and the space from our optimization program. We can optimize the trajectory spatially with no reference to how fast the missile goes along this particular path. What I've done is I've assumed that my reference trajectory can be written as the sum of a 7-order series of functions. Now, and each of these A's, A1, A2, is a function, and each of these variables is one of the Cartesian coordinates. So there's actually 3 sets of these. So for a 7th order system, we're going to have 21 boundary conditions. And then you see why we need computers to work this stuff. And then, so this is the shorthand notation of my representation of my system. The thing I'd like to point out is that this here is the actual reference trajectory of the missile that it's going to fly. This is the first, the second, and third derivatives of that spatial trajectory. It is not velocity, acceleration, and jerk. It is actually the first derivative of the position and the second derivative of the position. It's entirely spatially oriented. There is no time involved in this whatsoever. Well, now that I have my reference functions, I can solve them backwards and find the value of my particular trajectory functions. And each of those is one of 3. So there's 21 of these floating around. You see that these are all functions of the initial and final conditions. So by varying the initial and final conditions, I can change the trajectory significantly in some cases. And I'll show you exactly what I'm talking about here. What I've done is I've gone through and I've taken those 21 functions and I've assigned values to them, just general specific values. I'm varying the third derivative of the initial function on x1, and this is x1 and x2. Varying the third derivative of the initial function only. and I'm varying it with 4 different parameters, and I'm varying tau, which again is a virtual system, but in this case it might be easier to think of it as time. So I'm varying the time available from 1 to 10 seconds. And you can see that the path changes significantly. When tau is 1, I get almost a straight line. When tau is 10, I get a nice smooth arc. And the rate of change of these particular paths is varies significantly as well, as I change tau and as I change just this one variable. And imagine if I change all of them in rapid succession, I can very quickly find an optimal flight path given the particular boundary conditions that I'm working on. And that's what my algorithm does. Now, once we have spatially optimized this system, we need to bring it back into the time domain, and we do that through a function of lambda, which is the change in the virtual arc, delta tau, over the change in time that has occurred at that point. And basically, at every point on there, all of these, even though tau is a virtual thing, virtual arc, so it's not. So this is the same amount of tau as it goes across. And then the time derived is found from integrating the velocity as I go along, and then I take the velocity and divide by the distance traveled, and I come up with my delta time. And then by converting through this lambda, that brings me back from the spatial domain into the time frame. Now, the specific problem geometry of this particular function, I have my ballistic missile, which is traveling on its arc. I have my interceptor missile, which has just finished its own launch phase and is now ready to intercept the target. I'm assuming that I know the position and velocity of my ballistic missile, and I know the position and velocity and acceleration of my standard missile. What I've done is a simple first-order predictor for the ballistic rocket, and I'm going to choose an intercept time, and I'm going to choose it, and from that time I'm going to develop an intercept position. And then I'm going to that's going to become my final position. My final velocity is a function of the thrust of the interceptor missile. And then these two variables, my heading and my flight path angle, are what my computer model actually optimizes. I'm trying to get a 90-degree impact on the ballistic missile based on it being at this particular point. Now, normally a predictor guidance law would do exactly this and stop. But what my system's going to do is it's actually going to figure out whether or not this is a feasible intercept point. And if it's not, it's going to try again. And it's going to actually pick, it's going to optimize the time of flight, it's going to optimize the distance flown, and it's going to optimize the angle intercept. And it's going to do this in a predictive manner, but the prediction is significantly more accurate than a normal system because it's actually going to test it before it even implements it. So the program specifics, I have all of the data that I know and I have extracted. I know the dynamics of the flight, the ballistic, or the interceptor missile. I know how it operates in the physical domain. So what I've done, I'm developing my control time histories, NY and NC, which are the axial and the two coordinate axial controls. And then I have my constraints on the system, which are the maximum amount of G's that the missile can pull. What I've developed is a performance index, which is a summation of tau, time to go, and then a representation of the angle of impact. And by using scaling factors and weighting factors, I can vary the amount of each one of these that impact on the performance index. And my program goes through and minimizes this value of J, and the minimum value of J is going to be the optimum flight path. So in the next one, I'm going to show you a simulation of it working. It's going to take